Hi! In this video we're going to see some business applications of the first derivative test. Alright, so a classic example is using the first derivative test to analyze a profit function. Now let's say that I'm in the business of making items, and the total cost in dollars for me to make X items is given by this cubic function right here. I've purposely used some, not nice numbers here to emphasize the fact that you'll probably see those when you actually start applying these to real business situations. Okay, so this is my total cost. You can see my fixed cost right here, $165, and then my variable cost in terms of that cubic polynomial. And let's say that I'm selling each item at the per item price for $34.99. Buy now. Let's analyze my entire profit function using the first derivative test. The key question that I'd like to answer is positive profit possible? And if so, what is my maximum possible profit going to be? Alright, now the first thing that I would do on the first derivative test, step 1, would be take the derivative. But now I have to do step 0 because inside this application I want to analyze profit and I don't even have the profit function yet. Alright, so this is going to be secret step 0. Before we can get to step 1 of the first derivative test is going to be to write the total profit function. This is actually something that we practice in business pre-calculus, so I would actually really encourage you to pause the video right now, and given the things that we have on the board here, try to complete step 0, which would just be to write the total profit function, P as a function of X, so we can go on to step 1, which would be take its derivative. Did you do it? Are you trying? I hope that you're trying because you're going to need those skills. This is a real life example right here. So let's try to form our profit function, and hopefully for step 0 you recall that your profit is going to be your total revenue minus your total cost. Okay, well I've been given my total cost function right here, but this is a puzzle that I was wondering if you could solve this by yourself. What was your total revenue function? Did you figure that out? Well, I've given you a per item price here, and total revenue is going to be the per item price multiplied by the number of items. So this is going to be my total revenue function, and that's going to be in dollars, given X items. Okay? So now that I have my total revenue and cost functions, then I can form my profit function by saying my revenue, and then subtracting away my cost. And be really careful when you do this step right here. Make sure that you enclose the entire total cost function inside a set of parentheses, because you must factor that negative sign through when you're subtracting off the cost, and you don't want to mess that up, okay? So then make sure now in this step that you simplify right here. You're going to want to simplify, which simply means to combine the like terms. You can see we have this linear term, 34.95. Oh, wait. Oh, we don't even have any linear terms over there. Actually, there's nothing we really need to do to simplify here except to factor through the minus sign. If we had some like terms, like for instance, if we had a linear term inside this, we would combine those as well. But we don't even have any like terms. So in order to simplify this, I'm just going to rewrite this with the negative sign factored through, and I choose to write it in the highest order of X down to the lowest order of X. Mathematician's preference there. You don't necessarily need the terms in this order. You can have the terms any way you want mixed up, as long as you've got the minus sign factored through, or equivalently a parenthesis surrounding the total cost. Okay, so that's our secret step 0, so that we can go on to step 1. And step 1 is going to be to find the first derivative P prime of X. Alright, and go ahead and test your own ability by using the power rule, constant multiple sum and difference rules. What's the derivative there? Negative 0.03x minus 0.56x, oh sorry, that's x squared, and then plus 34.99. Okay, so is that what you got for the derivative? Hopefully that's correct. Alright, let's test your review. What is the units on P prime? This P prime is in units of, it's going to be whatever units P was in divided by whatever units X was in, okay? So P's in dollars and X is in items. So this is going to be in units of dollars per item, all right? Dollars per item. Nice. So that gets us to step 2 then. And what was step 2 in the process? After we find the derivative, then we have to locate the critical values. That's right, by setting it either equal to 0 or equal to does not exist. Now once again, if you recognize what type of function this is, what type is this? Polynomial, right? It's polynomial, so it always exists. So we don't have to worry about trying to think about when it does not exist. We just have to set in step 2, therefore, P prime is equal to 0 to locate the critical values. Okay, so these are the critical values, the values of X at which the derivative equals 0. Oh, geez. You think I'm going to be able to factor this one by hand? No luck there. So you're going to have to use the quadratic formula. Now I'm going to leave that to you to do on your side page there, but I'll just say you're going to use the old quadratic formula. And just for a quick review, what's the A? That's right, that's the coefficient of the quadratic term. What's the B? The coefficient of the linear term, including its sign. And what's the C? That's going to be the constant term right there. And then you're just going to crunch those through the quadratic formula, and then you're going to get conclusion that X is approximately negative 44.74, and the other root is X is approximately 26.07. Alright, so our critical points are located around negative 45 and 26. Remember, X is in terms of items, and I'm probably not going to produce a fractional amount of any item, so I'm kind of just in my head rounding these to the nearest whole number for this example. Now, are both of these totally valid values of X to consider? No, because again, X is a number of items, and so a negative number of items is not a reasonable thing to consider. So now when we go on to step 3, which is drawing the F prime, or in this case the P prime sign number line, we only have to really consider the one positive root, and that's because X is a number of items. Okay, so this is the approximate location of the root, but you're going to see that when I go to the last step where I conclude where I might have an optimal value of profit, I'm going to round this to 26 because you have to round it to the nearest whole number. There's no way about that. I'm not going to make 7/100ths approximately of an item. Okay, so let's fill out the P prime sign number line. Now what are we doing to fill this out? How do we know that it's going to be pluses or minus on either side? Remember, we have 2 different methods in order to do that, and I encourage you to use both methods because that way you can make sure you got it right. Method number 1, using test points, all right? So you can just use a test point, and over here, a convenient test point over here would be maybe X equals 0. You see how X equals 0 is less than 26, and it happens to be greater than the other root. Now, even though I knocked out this root because it doesn't make sense, that is not to say that that tick mark would not actually be on the number line. Be very careful with that. For example, on this problem, using a test point of X equals negative 1,000 is not a good idea because that would be on the other side of this tick mark, okay? So be really careful. Inside an application, if you're going to cut this off, where you're going to say my X has to be greater or equal to 0 because of domain issues in the application, don't pick a point that's on the other side of that, all right? But X equals 0, that's a valid number of items to make, 0, so I can use 0. So where would I plug in 0? Do you guys remember? What function would I plug in X equals 0 to? The derivative, that's right, you want to plug into derivative because it's a derivative sign number line. So if you plug in 0 here and here, you see why I chose 0 because it's the easiest number to choose? P prime of 0 is 34.99, okay? So when I plug it in, P prime of 0, that's 34.99. Alright, and so what am I going to put here? Little pluses or minuses? Plus, 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 that's right. Because it's positive. If it's positive for this, it's going to be positive for all the numbers. Go ahead and pick another test point like X equals 20. You'll find that it's positive as well. Alright, likewise, I can use a test point over here. Now here's where I could go crazy with it and use like x is equal to 500 million because it's on that side. And I like that crazy number sometimes because it's easy for me to plug in my head. If I have a huge, gigantic number right here and I choose to square it and multiply it by a negative, it's going to be a negative number. Alright, now this isn't going to make up for it, and this measly $34.99 is not going to make up for it. If I put in a giant positive number, because of this negative in front of the quadratic term, I will get a negative number. And it's as easy as that. I don't even have to actually calculate it. If you can use that logic and you're comfortable with that, that's how I can conclude the minus, minus, minus. Alright, now that's the one way to do it. Method number one to fill out the f prime sign number line is using the test points. What was the alternative graphical method? Graphing. I just said it. Okay, right. So if you actually graph, and you probably, hopefully at the start, wanted to take a graph of p of x, like I said, as soon as you get an equation, throw it in your calculator and graph it. That way you can pay attention and check that what you're doing algebraically is correct. You're going to see something like this. And it looks like it's got a peak right up there, and that peak just so happens to be right around 26.07. Looks like we're doing good because we have located a place with a horizontal tangent line right around where our algebra said it would be. Not only that, we can confirm that the signs on our f or our p prime sign number line are correct because look, the function's going up. It's increasing. That means its derivative is positive. It hits 0. That's where I ticked it off on my p prime sign number line. Then it going down, decreasing, so its tangent line is negative. That's a double check to make sure I've got step 3 correct. It's very important that step 3 is accurate before you move on to step 4. Step 4 is going to be classify. Alright, and classify using the first derivative test. Well, actually, it's easy to classify this because also as soon as I have the picture, I already know the answer is a max, right? That's another reason to have that picture with you when you're doing a problem. But also, according to the first derivative test, if the derivative goes from positive and it's going up, hits 0, and then goes negative, that's the top of a hill, that's a max. So you can classify as a max, classify the value, the critical value, x is approximately 26.07, as a max, a relative max. Okay, so sometimes they may just ask you to classify. Then you will say that critical value is a maximum value, relative maximum. Sometimes, especially when you're in an application, they may push you a little farther to actually say, what is the critical point? Remember, the critical point is an x comma y point, and that is really what tells you some additional information. In the case of this application, this is my profit in dollars over here. So how many dollars is my maximum possible profit? Now, because this is an application and I cannot make this fractional amount, I am going to round this to the nearest whole number first, and then I'm going to take the number 26 and plug it in order to get the y. Okay? Because if I want to know what my actual maximum profit could be, it's not possible to get the profit out of this little bit of the 700th of an item. The closest production level I can do is 26. So I'm going to take the number x equals 26, round it to the nearest item, and then plug it into the equation. Last question, which equation am I plugging it into? Am I plugging it into p prime? Am I plugging it into p? P, that's right. You're going to plug it in step 4 in your conclusion to get the y value. You plug it in right here to p of x. This is p of x right here. And another thing that could tell you that actually is if you plug that number into p prime, you're going to get 0, because that's where we started, right? That's how step 2 and 3 went. To find the critical points was the derivative was 0 there. So if you happen to plug in step 4 and you get y equals 0, that might tell you something. Think about that. You might have picked the wrong function to plug it into. All right? So in order to get the y coordinate, we plug it in back into the original function. And p of 26 here, you should find is about 379.7, all right? So that's my critical point, and more importantly, that's going to be my relative max. And max is important when you're talking about profit, because this is the most profit I could possibly make, is going to be $380 almost, and the best production level for me is going to be 26 items. And that's really important information. Now you may remember from pre-calculus that we solved similar problems like this using the quadratic formula when we had an equation that was a quadratic, but this equation is a cubic. And sometimes we'll have equations involving e to the x and square root terms and other stuff. So we don't have a vertex formula for that. The main general method we have for locating optimal values, whether they be highest or lowest, is going to be through calculus. Okay, so let's get one more example in here for business. And in this next example here, I'm going to give you an actual marginal function instead of a total function. And we're going to graph that marginal function and see if we can make conclusions about the total function. Okay, so for example, my marginal revenue as a function of x is given with this equation. Keep in mind, this is a marginal quantity. This is not a total quantity. Oh, sorry. Write it like this. It's 25,000 times 40 minus 0.2x divided by the quantity 0.2x plus 40 cubed. All right, so let's say that I've given you the marginal revenue function, and what kind of units would you maybe expect if total revenue was in dollars, and if x was a number of items, the marginal revenue would be in, remember the marginal revenue is analogous to the derivative, so it would be in dollars per item. All right, so this is how much my revenue is going to change at a production level of x. If I'm selling x items right now and I want to switch and sell x plus 1 items, my total revenue will change by this quantity, the marginal revenue. Okay, so let's try to analyze or see if we can get any conclusions about the total revenue from marginal. Now, I just want to look at this function for a minute. If this was the derivative of a function, would I know what function that came from? I don't know. That would be called integration, and we will touch on that at the end of this course. But for now, let me just say that if you're given the derivative, if you're given a marginal quantity, trying to derive where it came from, so what is the revenue function that when I took its derivative got down to this, that's a very hard question. That requires what we call integration. Okay, so we're not going to answer that question right now. We're just going to take a graph of the marginal revenue, and we're going to try to see what we can conclude from that. Okay, and I'd like you to take a graph of it too. Please try this on your own as well. And if you did, you may see a graph that looks similar to this, where it kind of goes down like that. And this is around 8 on this axis, which is in dollars per items. And it looks like it hits 0 right here at 200. The MR itself equals 0. What does this mean again? Like, let's say if I was at a production level of 100 items, and if my marginal revenue at that point was about, I don't know, 6.5, that would mean if I changed from 100 to 101, I would make $6.5 more in revenue. Okay, so that's what the marginal is. All right, but the whole topic here was actually the first derivative test. That's the topic of this week. So how am I supposed to get the number line and all that kind of stuff? How can I make any conclusions about this? Let's see. Well, what was step 1 in our 4-step process of analyzing Extrema using the first derivative test? Step 1, get the derivative. Oh look, we already have the derivative. Nice. So it's like step 1's already done for us. Okay, so then we're going to go on to step 2, which is where we set the derivative, in this case the marginal revenue, set it equal to 0 or does not exist. Alright, that's going to be step 2, and I can actually still do the problem even though I don't have the total quantity. I can still do the problem and make conclusions about the total quantity. That's what's amazing about it. Okay, so let's solve this out. When is this entire mess of junk? And keep in mind that if the 25,000 is out in the front, that actually means that it's on top of the fraction. So you can really see that function rewritten as this function with 25,000 on top. Okay, now to go over this again, when you have a fraction and you need that fraction set equal to 0, you gotta set the top equal to 0. If you want to know when it does not exist, then you set the bottom equal to 0. Okay, so we'll go through each of these separately. Let's start with the one where it equals 0. If it equals 0, the top equals 0. Another way for you to see that would be to conceptually multiply both of sides of the equation by the denominator. If I multiply this by the denominator, it would go away. If I multiply this by the denominator, it would still be 0. And I would be left with a statement that just the top needs to be equal to 0. You see, multiply both sides by that, it just disappears because of the 0. So really, I need that equal to 0. Well, if I need that equal to 0, I could also divide out by 25,000. Just divide out by that. And now I've got something that looks relatively easy. At first it seemed pretty hard, but once you kind of cancel some stuff out, that's all I have to solve. And so what I have to solve is just this linear equation. And so I'm going to divide that by 0.2 right there, and then get x is equal to 200 items. All right, what was that again? What would I keep calling this point? That's the answer to step 2. Critical value. That's right. This is the critical value of x at which the derivative is equal to 0. Okay, please note, I did not take the derivative of the function in step 1 because the function given to me was already the derivative. If you start this problem by firstly taking the derivative of this messy function, then you're in for it. You're going to have to do the quotient rule. It's going to get all messy. Don't start there, okay? The derivative is already given to us. So, step 2 was set what's already given to us equal to 0. Okay, now because I have a fraction, I must also address the fact that it does not exist. So down here, let's find out where MR is equal to does not exist. And remember, those would be places where I would be dividing by 0. So I'm not going to write down the whole function. When I'm looking for does not exist on a fraction, I'm just setting the bottom equal to 0, okay? So when would the bottom quantity, like this, cubed equal 0? Do you know how to solve that? The first step would be to take the cube root. So raise everything to the 1/3 power, or take the cube root. And after you do that, since the cube root of 0 is 0, you actually get to this statement. It kind of looks like that statement up there, except there's a plus instead of a minus. So it turns out when you solve this linear function, you get x equals minus 200 items. Minus 200 items, that doesn't make any sense. So I'm going to cross it out, and I am not going to consider it inside this application problem. If it wasn't in an application, I would have the negative value on step 3, my f prime sign number line, but not in this case because I'm inside an application. So the only things that count over here doesn't count. The only thing that counts is x equals 0 or greater. Okay, so now I'm going to tick off places where x equals 0 or greater and tick off my critical point, x equals 200 items. This is my critical value right here. And this is going to be the r prime sign number line. And now I'm going to draw it right underneath the function like I did before, but keep in mind that this is not a graph of revenue. This is a graph of marginal revenue, which is the same thing as the derivative. Okay, the derivative of revenue with respect to x is the marginal revenue. So now, if I want to do, again, my two methods where I determine the sign and the sign prime number line, I can do first the analysis, then the graph. Okay, first the analysis. I have to pick a test point between 0 and 200. 0 counts. 0 is actually I shouldn't even write that. Like I said before, you don't want to tick off 0 because it's not a critical point. But it's inside the domain of the application. Okay, so if I put x equals 0 in here, you can see I get a positive number out of it. And so using the test point, and plugging the test point back into this function because this is already the derivative. All right, the r prime sine number line is the same thing as the mr sine number line. I get positive. And now at this point, if you are comparing that with the graph you see, you might say, hey, wait a minute. If I look at the tangent line to this graph, this is decreasing. So I should put a minus here because it's decreasing, right? Or what? I'm confused. What's going on? Do you guys understand what's going on right now? What's going on is that I'm already graphing the derivative. This is what's different than the previous problem. I'm not graphing the total revenue. I'm graphing its derivative, the marginal revenue. So the signs that I draw on the r prime sine number line will correspond to whether this graph of the derivative is positive above the x-axis or negative below the x-axis. We really have to pay attention to exactly what we're graphing and what we're looking at when we do the analysis. Okay? In this case, we've got a graph of the derivative already. Is it positive over here? Yes, because it's above the x-axis. Its tangent line doesn't have anything to do with this. In fact, the tangent line to this graph is what we would call the second derivative, because it would be the derivative of the derivative, and we'll get into that later, okay? So for now, I just want you to understand the r prime sine number line is the same thing as the mr sine number line. And mr is positive because on a graph of mr, that's greater than 0. Likewise, the graph is below 0 here, which leads us to negatives. The alternative method would be to do an analysis by doing a test point. Let's say x is equal to 300 or maybe 1,000 even. If I plug in a large number for x up here, the numerator becomes negative and the denominator stays positive. Negative over positive is negative, so by analysis I can also see the negative there. Okay, so now let's make a conclusion in step 4. And once again, I do not have a graph of the total quantity. I can't really say exactly what the total quantity is without using integration, which you haven't learned yet, to bring it back up to what it was. Alright, but I can still draw conclusions about the critical value of x equals 200. X equals 200 is a... What's the classification? You can't look at a graph of r because you don't have a functional form of r. So now you're forced to use a first derivative test. What kind of extrema is it? Let's see, it goes up, then it's going up, and then it hits a 0, and then it goes down. Relative maxima. That's right, so this is a relative maximum. Yay. We can't get the critical point. We have the critical value. We've classified the critical value, but we can't get the critical point because we don't have the total revenue function. Okay? But at least we know that this is a relative maximum, and that already says a lot because it basically says that if I want to maximize my total revenue, a sales level of 200 items is what's going to do it. So my conclusion here is that total revenue is maximized at a sales level of x is equal to 200. That's the best conclusion I can make.